Thank you for the warm welcome. Thanks very much for the invitation to be here. I was last here almost exactly 5 years ago to give a high energy theory seminar. The day before the seminar, I contracted something like food poisoning, and I actually didn't get better until about a week after I went home. But I remember that during the seminar, I so much enjoyed the scientific exchange with this community that for 1 hour, I felt completely happy and healthy and whole. So it is really a delight to be back. Thank you.
Oh, I forgot to say one last thing. Nicole wrote an amazing, critically acclaimed book called Quantum Steampunk, and I highly recommend it. I read it myself, and I even gave it a blurb. So I just forgot to say, it's a really good read for the summertime on the beach. Sorry.
Thank you for the background. Related to quantum steampunk, you might be wondering about this kind of unusual figure here. So it's here because I think of this talk as really not your stereotypical great-great-grandmother's thermodynamics. What is our stereotypical great-great-grandmother's thermodynamics for background? It was encapsulated eloquently by a writer, Sam Keen. He said that when he was a student studying physics, his thermodynamics class opened with a quote from Einstein. Thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown. This sounds like quite the ringing endorsement from Einstein. So this writer, back when he was a student, was very excited. But even Einstein's imprimatur couldn't glamorize the grubby details of heat and work exchanges. So according to this writer, thermodynamics, despite being arguably the most successful scientific theory in history, nobody cares about it because it's so incredibly boring. So am I doomed to bore you for the next 50 minutes? Well, let's take a step back and review what thermodynamics is. It's basically the study of energy, heat, work, and transformations amongst the possible forms of energy. Now, this writer complained that the name thermodynamics evokes images of Victorians in stuffy suits tinkering with steam engines. So I agree about the images of Victorians in suits, but I don't think that they were all very stuffy. So in fact, thermodynamics was inspired by the Industrial Revolution, which transformed civilization. For the first time ever in history, there were factories powered by engines. Productivity jumped. So naturally, people wanted to understand how efficient these engines could operate. So thermodynamics was developed with a practical bent, but it ended up inspiring studies of fundamental questions like, why does time appear to flow in only one direction? As well as wonderful science fiction takes on the possibility of times not flowing just in one direction. Now, this writer, Sam Keen, also complained that thermodynamics is a far cry from the enigmatic koans of quantum mechanics, which everyone can see is clearly very fascinating. So, over the past 3 decades, the enigmatic koans of quantum mechanics, what makes quantum theory really weird, has been codified in quantum information science. By quantum information science, I mean the study of how we can use quantum phenomena to process information in ways impossible if we just have classical systems. By quantum physics, I mean a number of things. So entanglement, strong correlations between particles, the non-commutation of operators, the discreteness of spectra, how measurements disturb quantum systems, and even more. By process information, I mean solve computational problems, communicate information, secure information cryptographically, and store information in memories. Just as there are information processing tasks, such as computation, there are thermodynamic tasks, such as powering cars and charging batteries and cooling systems. Since we've seen through quantum information science, quantum phenomena can enhance information processing tasks, we also need to ask, how can non-classical resources enhance energy processing tasks? For example, we can define quantum engine cycles, and some of these engines can outperform their classical counterparts according to certain metrics. The laws of thermodynamics were developed in and around the 1800s to describe steam engines, large classical systems. But we can extend them to see how they should apply to small and quantum systems, especially using the tools of quantum information theory, which, for instance, have been used over the past few years to derive from quantum theory and more refined, more detailed variations on the second law of thermodynamics, which helps us understand why time flows in just one direction. Finally, we can look at systems that are processing energy and other thermodynamic quantities and ask, what behaviors do these systems exhibit only if they're quantum? So we can use thermodynamics to understand anew what the difference is between the classical world and the quantum world. So these three questions form what I think of as the guiding questions of the field of quantum thermodynamics, which is more or less my home base. This field has exploded over the past 15 years, in large part because the tools of quantum information science have been well developed, and we can now apply them understanding energy processing quantum systems through how they store and process information. So if you're interested in the field of quantum thermodynamics as a whole, I can recommend these two reviews, which provide nice overviews of this kind of more modern quantum information steeped version of quantum thermodynamics. And there's also the book that Stefan mentioned, which was written kind of for the general public, including scientists. It's basically in the form of kind of a conversation we might have over lunch if you sat down with me and asked, what is quantum thermodynamics all about? I probably should spend a minute explaining the name. So steampunk is a genre of literature, art, and film. It takes settings from the 1800s like Victorian London, Meiji Japan, the American Wild Wild West, and juxtaposes those with futuristic technologies like time machines and automata. So think, again, of H.G. Wells's The Time Machine. I see quantum thermodynamics as the real-world incarnation of steampunk because we have thermodynamics from the 1800s together with quantum information science, which is partially cutting edge and partially futuristic, since we don't yet have full-scale quantum computers. So basically, to amuse myself, I peppered this talk with a bunch of steampunk artwork. If steampunk is not your favorite aesthetic, I'm sorry, but it kept me amused, so hopefully it'll at least keep you awake. Now, for most of this talk, I want to focus on one small growing subfield of quantum thermodynamics. It was motivated by basic undergraduate statistical mechanics. In undergraduate statistical mechanics, we often think about a small system interacting with a big environment. The two exchange things. If they exchange just heat, the small system may thermalize to a canonical state. If they exchange heat and particles, the small system may thermalize to a grand canonical state. But probably first, I should explain what I mean by quantum state. It's not just a wave function that represents a special class of states called pure states. These are states of systems not entangled with anything else. More generally, a quantum state can be represented by a density operator, which you can think of as a matrix relative to your favorite basis. Technically, it's a trace 1 positive semi-definite linear operator. Trace 1 means if you measure the system, you'll obtain some outcome. Positive semi-definite means if you take this matrix and you calculate its eigenvalues, you'll find that they're all real and at least 0. And the linear just means this is a particularly simple operator. Okay, so if you have your small system and big environment exchanging both heat and particles, the small system can thermalize to the grand canonical state. For example, suppose that you take your cup of tea that we just got from the snack table, you set it on this part of the chair that folds over, you let it sit there for a while. It's going to cool down. It's going to come to be at the temperature of this room, in which case we will say that the system has thermalized. And it'll also exchange water molecules with the air around it. And we can play the same game for the exchanges of many different quantities. These things that are exchanged by the system and the bath are conserved globally. So we call them charges. I'll denote them by Q and index them with A. This process, this exchange, leads to thermalization, which is ubiquitous. It happens all the time. And everyone here at some point is going to die and thermalize. And again, if you have a hot cup of tea or coffee, it thermalizes while exchanging heat and water molecules with the air around it. So thermalization is ubiquitous, in part because it goes hand in hand with the arrow of time. If we can observe nothing but your cup of tea, then we will know time is passing because we can observe the temperature dropping. In quantum statistical mechanics, we represent these exchange things with Hermitian operators. So the system of interest has a particle number operator, the environment has a particle number operator, and so the small system will have one Hermitian operator associated with each of those charges. It turns out that we implicitly assume in some important arguments that these Hermitian operators commute with each other. This assumption is really not mentioned. It certainly wasn't mentioned in my undergraduate statistical mechanics class. But it turns out to lie behind some derivations of the form of the thermal state and the Onsager relations, which are important results about the near equilibrium regime. But yes? Then this is a very relevant place to be giving this talk. Good to know. But one of the most fascinating parts of quantum theory is the importance of operators that don't commute with each other. This lies behind measurement disturbance and quantum error correction and all sorts of interesting quantum phenomena. So we're kind of obliged to ask, what happens to thermodynamics if the system and environment exchange charges that don't commute? This question has led to a small growing subfield. My group just published a paper about it in Nature Reviews Physics, a perspective on this little field. So here's where I'd like to go in the rest of this talk. First, I'll give you a simple example of a system and environment that exchange these non-commuting charges. Then I'll present a little historical overview of the study of this question. I'll talk about what changes physically in thermodynamics when charges don't commute. And then I'll talk about opportunities for future work, of which I think there are very many. So what's a cartoon, a picture that we can keep in our heads? This example was proposed in this theory paper, which was then realized experimentally in Rainer Blatt and Christian Russ's trapped ion lab in Innsbruck, Austria. And an extension of this relatively simple example to many other systems and many other charges appears in this theory paper. So suppose that we have a chain of qubits, quantum two-level systems. These can be realized, for instance, as two different internal states of an ion. The system of interest can consist of some small number, maybe 2 of the spins. The whole system consists of n copies of this small system of interest. The other copies form the effective environment. So we can regard the whole thing as a closed quantum many-body system and look at what happens inside of it. In order to introduce some natural charges, I'll denote by sigma aj the eighth component of the spin of qubit j. We can form global charges by taking one component of the spin and summing it across the lattice for each of the 3 components. Now we need a Hamiltonian, we need dynamics, with 3 properties. First, the Hamiltonian should conserve all of these non-commuting charges globally. Second, the Hamiltonian should transport the charges locally. And third, if we're going to give this system as good a chance as possible of thermalizing, then the Hamiltonian should be non-integrable. Basically, it should be able to get the state vector, the state of the global system all over the state space. We can build such a Hamiltonian. We all know the forms from quantum physics class of the raising and lowering operators for the z component of the spin. We can build an operator that takes one quantum of the z component of the spin from site j plus 1 and hops it onto site j and does the reverse in superposition. Similarly, we can build these hopping operators for the x and y type charges. In building the whole Hamiltonian, we should take our hopping operator, sum it over our charges, and then sum over the lattice. and introduce a hopping frequency. Now you might recognize this factor as the Heisenberg interaction. The Heisenberg interaction has been well known for a long time. Again, it can be simulated experimentally. Although I really like the fact that even though the Heisenberg Hamiltonian has been well known for a very long time, even over the past decade or two, it has been shown to have some surprising transport properties. So it is still a very interesting operator. But I never see it written like this to show that explicitly it conserves non-commuting charges globally while transporting them locally. And if you think the Heisenberg interaction still is too boring, then you can take this template for building up a Hamiltonian that conserves non-commuting charges globally and transports them locally, and extend it to build Hamiltonians for many other algebras of charges. If we want to make this Hamiltonian non-integrable, then we can extend the couplings to be beyond nearest neighbor, or make the lattice more than one-dimensional to give the system the best possible chance of thermalizing. So that's a picture that we can all keep in our heads. Does anyone have questions about it?
So this chain is not coupled to the environment?
No, part of the chain is serving as the environment of a small portion of the chain. Because the idea is, whenever we have a system in an environment, we can always just step back and see that the whole thing is itself a quantum system.
Temperature defined in this case?
It's through this relation. So we take, let's say that psi is the initial state. We take the expectation of the value of the Hamiltonian in the initial state, and this is conserved, and set it equal to the expectation value in the appropriate thermal state, which I'll show you. We write the analogous equations for all of the other charges. This contains our temperature and analogous properties.
So you implicitly, by writing it this way, you already assume this chain is embedded in some thermal bath with a temperature T.
So instead of assuming that it's embedded in a thermal bath, we wanted to see if thermalization emerges. So the whole point of the experiment was to see, is this thermal state a good prediction for the long-time state of the small system of interest? And the experiment showed that it actually was a good prediction. Right. So here's a little bit of history of this question of particularly quantum thermodynamics. The first mention that I know of anything like non-commuting charges in thermodynamics appeared in this 1957 paper by E.T. Jaynes. In this paper, and version 1 of the paper, Information Theory and Statistical Mechanics 1, Jaynes codified the principle of maximum entropy. It shows that the thermal state of a system is the state that, upon satisfying constraints that we know about it, achieves the maximum entropy. One constraint on every quantum state is normalization, but we might also know, for instance, the expectation value of the energy, the expectation value of the particle number. The relevant entropy is the von Neumann entropy, which quantifies kind of our average uncertainty about the outcome of a certain measurement of the state. So if we maximize the von Neumann entropy subject to these constraints, we find that the state that achieves the maximum is the appropriate thermal state, which is in this case the grand canonical state. Jaynes noted that this principle of maximum entropy can be applied even if the observables we know about don't commute with each other. And that was almost all he said. He had one paragraph about this non-commuting case, and when I saw it, I was like, how could you stop there? This is the most interesting part. No one in our courses and our textbooks ever talks about this non-commuting case, but it's so particularly quantum. So he didn't talk about thermalization or physical realizations. He wasn't even necessarily talking about a whole lot of physics. So he was talking more about what we know and the information that it's reasonable to ascribe to a system. He had some acolytes who did this follow-up work. They tried to derive the state more physically, but ran into a mathematical roadblock. Over the next few decades, nothing happened with this question. I think the community totally forgot about it. there were some mathematical developments in quantum information theory that would turn out to prove useful later. Then a few years ago, in the intersection of quantum information and quantum thermodynamics, a few of us realized in some of our derivations, we were assuming that charges commuted with each other. But why were we doing that? Just because the math worked. But we really shouldn't be doing that, because so much of quantum comes from non-commutation. So these realizations spurred 3 different groups, all at the same time, to try to justify the writing down of a thermal state. Again, Jaynes had this really information theoretic argument, but there are more physical ways to derive the thermal state's form. We all ultimately agreed that it makes sense to write down the form of a thermal state. We call this the non-abelian thermal state. In other fields, you might call it a generalized Gibbs ensemble. The non-abelian is here because if you have charges that don't commute with each other, they generate a non-abelian algebra. So the state has a form you might expect. It has an exponential. This beta is the inverse temperature we can ascribe to the environment. H is the Hamiltonian. Mu A is something analogous to temperature or chemical potential. QA is a charge, and Z is the partition function, which normalizes the state. Over the next few years, non-commuting charges started to propagate out into the intersection of quantum information theory and thermodynamics, and then after that, into other fields, like atomic, molecular, and optical physics, condensed matter, and some high-energy theory. So what happens? What have we learned? What happens to thermodynamics when charges fail to commute with each other? I'll present a small glimpse of what the community has learned now. And the takeaway of this part of the talk is that it isn't obvious that the small system should thermalize as usual. And this thought should surprise us because, again, thermalization is ubiquitous. It happens even to our teacups. It takes something special to stave off thermalization or change it. So as I said before, there are derivations of the thermal state's form that break down. Also, these global charges, since they don't commute with each other, don't share an eigenbasis. So they might not share any eigenspace. It's a shared eigenspace that can serve as a microcanonical subspace. I should review what a microcanonical subspace is and why it's important in thermodynamics. Suppose we go back to the simpler problem in which the system and environment exchange just heat and particles. Suppose we want to convince ourselves that the small system really is in a thermal state. Well, suppose that the global system has a well-defined particle number. So it's in a particle number eigenspace. And we'll also suppose that the energy is pretty sharply defined. We will ascribe, so this eigenspace that we've just described is called a microcanonical subspace. We ascribe to this global system a microcanonical state, which is the projector onto the eigenspace normalized by the dimensionality of the eigenspace. So we trace out the environment to get the reduced state of the small system of interest, and that turns out to be the grand canonical state, the appropriate thermal states, if the system and environment couple together just weakly. Now suppose that the system and environment exchange more commuting charges, then the microcanonical subspace will be an eigenspace shared by those charges. And apart from the energy, the Hamiltonian is special because it generates the time evolution. But we just said if the charges don't commute with each other, they don't share an eigenbasis, so they don't necessarily share an eigenspace or many eigenspaces. So we can't rely on a microcanonical subspace. So we can't rely on the very first step in our argument for the thermal state of the small system of interest. So why should we expect the small system to thermalize as usual? In addition, if the global Hamiltonian conserves non-commuting charges, the Hamiltonian is degenerate. Some of the energies equal each other. This is because of Schur's lemma, a result in group theory. And degeneracies tend to throw wrenches in arguments for thermalization or mixing. Now, we can imagine two thermal systems. Suppose that we have a rod with a hot end and a cold end. So these are thermal systems with two different temperatures. And suppose that heat can flow between them along the rod. Heat will mostly flow from hot to cold. And as energy leaves a system or enters a system, it generates entropy. Or more generally, as charges leave systems and enter systems, they generate entropy. And this entropy production goes hand in hand with the thermalization of the whole system. Now we can suppose that instead we have thermal systems that exchange non-commuting charges. We can calculate the entropy production and find that it is decreased by a term that depends pretty explicitly on the commutator of the charges. Yes? What is the state of the whole system? What? To be completely certain, I would have to go through the argument, and I would be interested in doing that. My guess is, do they take the limit as the number of systems, the number of small subsystems approaches infinity? Okay, so that's the issue. So also the arguments that, basically my overall takeaway from dealing with this little subfield is if you take the limit as n approaches infinity, then the non-commutation ends up not mattering. But if you just have a number of copies n that is decently sized but not infinite, then there should be corrections. There's this very interesting result by my colleague Iman Marvian at Duke. He was thinking about, suppose you have local operations, such as 2-qubit unitary gates in a quantum computer, and consider the set of all n-qubit unitaries on some large system of n qubits. So consider trying to implement the n-qubit unitaries with your local operations. If there's no restriction on your local operations, you can implement all the n-qubit unitaries. This is why quantum computers are universal. Now suppose that your local operations are constrained to conserve some charges. And consider the set of n-qubit unitaries that conserve those charges globally. Now you can no longer implement all the global charges with the local operations. And if the charges don't commute with each other, the constraint is even more severe. So in some sense, non-commutation of charges restricts a system's ability to achieve something kind of like chaotic behavior, but to get the state all over the state space. And finally, the non-commutation of charges conflicts with the eigenstate thermalization hypothesis, which I'll go into more detail about right now. The eigenstate thermalization hypothesis, first of all, has a horrendously long name, so it is sometimes abbreviated as the ETH. It's a toolkit developed in many-body physics, now used across many subfields. It's one of our best ways of understanding how a closed quantum many-body system thermalizes internally in the following sense. Consider your favorite typical local operator O. We can represent it as a matrix relative to the energy eigenbasis. The ETH is an ansatz for the forms of the elements of this matrix. Suppose that we have a Hamiltonian and an operator O that satisfy the ETH, and the Hamiltonian is non-degenerate, and we start off our global system in a microcanonical subspace. Then we can conclude, we can deduce that the system will thermalize internally. Consider measuring this operator's expectation value at some time t, and then averaging over time. This time average expectation value will equal the thermal expectation value to within small corrections. Here, n is the size of the global system, like the number of qubits or number of particles. And I'm going to use O in the sense of many body physicists like scales as. Quantum information theorists use O a little bit differently. We already said that if the Hamiltonian conserves non-commuting charges, it will have degeneracies. We've already said if the Hamiltonian conserves non-commuting charges, we cannot rely on the existence of microcanonical subspaces. So what about the ETH? What about our last postulate? Unfortunately, non-commuting charges also conflict with that. From now on, I'm going to focus on charges that are components of the angular momentum, maybe the spin angular momentum. We said that the ETH is an ansatz for the form of the elements of matrices, of local observables or operators relative to the energy eigenbasis. But the Wigner-Eckert theorem is, in fact, a statement of the forms of the elements of matrices that represent exactly those operators. So what is the Wigner-Eckert theorem? It's something that we learn on the way to qualifying exams in grad school, and then some people use it later and some people forget about it. I hadn't used it very much in research until this project, so I needed a review too. So in order to introduce it properly, I have to introduce quite a lot of formalism, which I don't have time for in a colloquium, so I'll give a simple example. Suppose that we start off with an atom that has some amount of angular momentum. The atom absorbs a photon. Then we ask later, what is the probability or probability amplitude associated with the atoms having some possibly different amount of angular momentum afterward? Now, this transition amplitude, its form is dictated by the Wigner-Eckert theorem. It's supposed to be the product of two particular factors. But this transition amplitude is also a matrix element. So the Wigner-Eckert theorem butts heads with the ETH because both are trying to predict the form of this matrix element. The Wigner-Eckert theorem is a theorem. It's been proved. It's definitely true. On the other hand, the ETH is just an H. It's just a hypothesis. So the Wigner-Eckert theorem wins out against the ETH. So we said if we start with these three postulates, then we can deduce internal thermalization. Now, all of the postulates are out the window if charges don't commute with each other. So are we doomed to give up the ETH, one of our best ways of understanding internal quantum thermalization, when charges fail to commute? So I had the privilege and pleasure of working with Mark Strednitsky's group on proposing a non-abelian eigenstate thermalization hypothesis that accommodates non-commuting charges. So here's a cartoon version. Again, if I were to present you the whole version, then I would have to present a lot of formalism that I can't present in a colloquium. So here's the overall form. Again, we're interested in our favorite local operator, O. We represent it as a matrix relative to an energy eigenbasis. Here's an element of the matrix. We postulate that that matrix element equals a coefficient times the sum of two terms. One term is called the diagonal term because it's non-zero only on blocks along the diagonal of the matrix. And the other is very creatively called the off-diagonal term because it can be non-zero even off the diagonal. This diagonal term encodes how our favorite operator's expectation value at time t behaves on average over time. The off-diagonal term encodes fluctuations about that average over time. This coefficient ensures that this ETH is consistent with the Wigner-Eckert theorem. And now all parts of this hypothesis depend on spin-related quantum numbers to encode the symmetry, the charge conservation, directly in the ETH. So how can we use this, or what do we learn physically from this hypothesis about thermalization? Well, let's go back to our premises in our earlier conventional argument from the ETH to thermalization. We said we needed to assume the ETH and non-degeneracy of the Hamiltonian and an initial microcanonical subspace. We've dealt with these two problems by introducing the non-abelian ETH, but we still need to deal with this problem, that our charges, since they don't commute, don't necessarily share a microcanonical subspace. So let's generalize the notion of a microcanonical subspace. Let's generalize it to an approximate microcanonical subspace. Instead of having sharply defined values, all our charges will have just fairly well-defined values. So consider measuring any charge QA. Suppose that the possible outcomes are arrayed along the x-axis. Along the y-axis, we'll sketch the probability density. And for each charge, that probability density should be peaked around the expected value, which is the analog in our problem of the total particle number in the ordinary grand canonical thermalization problem. This width should be not too great, so all of the charges should have bounded variances. You might wonder if such a state is at all realistic to prepare in a lab. It is. For instance, product states fall under this class, and so in the experiment in Innsbruck, the experimentalists prepared particular product states. All right, now we've rectified all three of our problematic postulates. Let's put together our non-abelian ETH with this approximate microcanonical subspace and see what we can infer about thermalization. What we need to do is compare the thermal average of our favorite operator with the time-averaged expectation value of the operator. So the thermal average follows from taking the trace of our favorite operator with the appropriate thermal state, the non-abelian thermal state. To get the time average, we start off the whole system in an approximate microcanonical subspace. Then we take the time t prime expectation value of our operator at some time t prime. We average over times, and then we take the limit as t approaches infinity. This is the time average. Let's compare the two. We can compare them in different regimes. First, suppose that the magnetization is as large as possible. It grows like the system size. In this case, you can show that the time average does equal the thermal average to within the usual small corrections. However, the argument is a lot more complicated than usual. Usually it lasts about a page, and in this case it lasts for several appendices because you have to check all these different cases because of the different symmetry properties that different operators might have. Now let's go to the opposite extreme and suppose that the magnetization is 0. There are multiple settings in which the time average can equal the thermal average just to within these larger corrections. These corrections are larger than usual polynomially in the global system size. So the corrections don't vanish immediately like exponentially, but they're polynomial, so hopefully they're visible. And this statement can be proved under an assumption that we argue to be physically reasonable. And we're now working on numerics to try to observe that, a case that satisfies this assumption. And I think this result is interesting for a fundamental reason and the possibility of an application. If the system doesn't get quite down as far as usual to the thermal states, then it's like the system isn't thermalizing as much as usual, and since thermalization goes hand in hand with the arrow of time, it's almost as though the system doesn't quite feel the arrow of time as much as usual. Also, if the system isn't getting to the thermal states, a fixed point of the dynamics, quite as much as usual, maybe the system is retaining some extra information about its initial conditions. So maybe we could use this non-commuting charge property to enhance quantum memories for a quantum computer down the line. Any questions now?
I have a question.
Yes.
some point you're probably going to give us an example of a non-commuting charge. So could it correspond to the same charge, not commuting, for example, or does it have to be different charges?
So my favorite example of the non-commuting charges are the ones that I showed earlier, the x, y, and z components of the angular momentum.
Okay, that's good enough. All right,
Okay, great.
I wasn't paying attention.
No worries. It's late in the day. Yeah.
Quick follow-up question. So by how much can it be away from the usual expectation of thermalization? You're saying it's reduced. By how much? Like, what's that's the limit? You said that's
Yeah. Usually the correction is like 1 over the global system size, and now it's like 1 over the square root of the global system size. That's an interesting question. I'm not aware of work on putting together the ETH with a critical system, or I guess the extent to which a critical system is thermal. I'm just not familiar with that. That's an interesting question. Yep.
So when you said a small system may not follow the usual way, the Boltzmann's way of thermalization, are you saying if I look at it, let's say I have a long spin chain, and then look at, let's say, a subset of this spin chain, then let's say if I initially create a certain dominant energy in a particular magnetization, let's say all the spins point up, and then, but if I allow the system to equilibrate, then the system should give me up and down with equal probability. You said that this may never happen for this two spin, so the system can never truly thermalize.
So this is a statement about the time averaged expectation value. I agree that it would be interesting to look at what happens at particular times.
So if we go back to Boltzmann's, the picture you draw, the original Boltzmann thermal heat bath argument, that the probability of my sample, which is small, in the big bath, the probability of finding the sample in a particular eigenstate is controlled by the multiplicity of the bath. You said this argument may not hold.
So in this particular setting,
which part is being challenged? So if you go back to the picture of drawing a small in a big one, so which part of the original Boltzmann's heat bath argument may be challenged when you consider quantum mechanics?
so I've talked about two particular arguments that are challenged. One is if you assume that your Hamiltonian and your operator through which you use as kind of a lens to view thermalization, if they satisfy the eigenstate thermalization hypothesis, usually you can infer that the time averaged expectation value here of the operator will equal the thermal expectation value, so trace of O with the appropriate thermal state, plus corrections that are like 1 over the system size. So that's a very specific argument, and that's a specific argument challenged by non-commuting charges. It's recoverable in one regime, but not necessarily in all regimes. Like we found a counterexample under certain conditions. So there is the correction to the thermal prediction can be larger than usual in the presence of non-commuting charges.
I would accept that if you take the Boltzmann's heat bath, you shrink it in such a way the degrees of freedom is of, let's say, not in 10 to the 22 bigger than your sample, but only, let's say, only a factor of 100 times bigger than, then I can see that you can have a breakdown of the equilibrium process.
Yeah, related to an earlier answer to Dimo's question, if we take the large system limits, then the effects of non-commutation shouldn't show up. So we're talking about systems that are decent size, but not in the large system limit.
So small systems, small heat bath, and then there's a big fluctuation.
Yeah, or we think about a large but finite size, definitely finite size systems. Okay, there are lots of opportunities for future work in this growing subfields. My favorite one is a puzzle. So now we have a number of results about what happens in thermodynamics when charges fail to commute. One little pile of evidence suggests that in some ways non-commutation of charges hinders thermalization, but another pile of evidence kind of suggests the opposite. So in the hinder camp are the 6 pieces of evidence that we just saw, that thermalization seems not entirely to happen as usual if charges fail to commute. But again, there are pieces of evidence pointing oppositely. Suppose that we look at the whole system, the system and environment composite. That's one really, really big quantum system. And we can imagine cutting it and asking how entangled are the 2 parts with each other? Because entanglement plays an important role in quantum many-body thermalization. And it turns out that non-commutation of charges can enhance the average bipartite entanglement in the whole system. Second, there's a regime of matter that exists at least for finite-sized large systems called many-body localization. In this regime, energy and information really stay localized for long periods of time. You can take a many-body localized system and force non-commuting charges on it. The non-commuting charges destabilize the localization. So even a very tiny stray field that's added can break the localization so that the system will thermalize quickly. Finally, some Hamiltonians have algebraic structures called dynamical symmetries, and they single out some special observables that will resist thermalization for long times. Shayan Majidi is a PhD student of mine, and he showed that if you take a system with these algebraic structures and you force non-commuting charges on it, then it eliminates the dynamical symmetries, so these special observables are no longer special, they'll just thermalize as usual. So all of these results technically don't conflict with each other because they were derived under different specific settings, but conceptually they really seem to clash. So I think a very exciting opportunity is to reconcile them and see how these very different perspectives are somehow married. In case you can't tell, I am hoping that the hindrance of thermalization camp sort of wins out. In addition, I think we should go to every single phenomenon in chaos in thermodynamics and ask what changes here or doesn't change if our system has charges that don't commute with each other. There are lots of phenomena to study, especially since quantum information theory has recently been leveraged to uncover new facets of quantum many-body thermalization and quantify different facets. A lot of works that have been done have been about equilibrium. And so now is a good time to move into dynamics of non-commuting charges. And also, a lot of work on non-commuting charges has been done within quantum thermodynamics. Now is a good time to spread the influence to other fields. In particular, since I know there are people here with strong high energy and nuclear physics interests, I'm very curious as to whether non-commuting charges are applicable to gauge theories. Gauge theories, we often say, have local symmetries. A symmetry is equivalent to conservation of some charges. Some gauge theories have non-abelian symmetries. For instance, quantum chromodynamics describes the strong nuclear force and has an SU3 symmetry. Also, my friends in high energy physics tell me that there are some really serious problems with our understanding of thermalization, like in high energy collisions of nuclei, thermalization happens much more quickly than expected, than predicted by models. Kind of the strange thing is that in gauge theories, the symmetries are local. In the thermodynamics that we usually have in mind, the symmetries are global. So it isn't, and well, local symmetries are technically global, but still they're kind of different paradigms. So I'm not entirely sure how they should go together, but I think they should. So in summary, we talked about charges that don't commute with each other in quantum thermodynamics. This is a particularly quantum version of thermodynamics. We can take a common setting taught about in classes and textbooks, add one little non-commutative tweak, and our expectations about thermalization break down. A simple example consists of a spin chain with 3 spin components that don't commute with each other. We saw some of what changes in thermodynamics due to charges non-commutation. In particular, the eigenstate thermalization hypothesis, one of our favorite ways of understanding thermalization in quantum many-body physics, breaks down. And its replacement, the non-abelian eigenstate thermalization hypothesis, allows for some anomalous thermalization. And most importantly, there's a lot more to be done here. This is the perspective on this little subfield that I mentioned before. My group has been fairly obsessed with this topic for a few years, so here's all our work in case you're interested. Also, if you want more of a story perspective on how this field began, that story is told in chapter 12 of this book. So, thanks for your time and attention.
Asking a real experimental manifestation of this non-thermalization. Are you suggesting that if we look at this particular local magnetization, if it's truly thermalized as a function of time, I suppose it is 0 magnetization. But if you go ahead and measure as a function of time, are you saying the lifetime that may be actually very long? Is that the manifestation of it?
I think we would need to start with a different setup and observe a different observable.
Let's say I take a magnetization, one-dimensional chain of spins. I just locally, I just put a pulse to polarize the spin up, and then go watch as a function of time. Let's say I have a way to measure the spin as a function of time. And I expect, according to what we learned in the standard thermodynamics, this would decay exponentially by following the standard divide relaxation. Are you saying this will break down?
No, I'm not saying that that expectation breaks down for a few reasons. So one is the results that I showed here were not about thermalization as a function of time, but the time averaged expectation value is a function of the global system size. So it's not how our signal decays in time, but rather as we grow our global system size, and each time we have a particular system size, we look at the time average. I'm saying that that has the possibility to behave differently than expected. And I totally agree with you that we have really strong intuitions about the setup that you described. And I'm not saying that those intuitions are wrong. Rather, I'm saying that there seem to be some conditions such that if we start in this particular state and we look at this particular observable, then we can see something anomalous rather than the standard setup and standard observable that you just described. So I'm saying you're right.
But we knew this all along, right? So when we were taught about the thermalization process, we were warned that this thermodynamics only works for n goes to infinity. If n doesn't go to infinity, of course it doesn't work.
So there's a specific prediction about finite n that's kind of conventional that comes from the eigenstate thermalization hypothesis. And it states that the time average equals the thermal average plus corrections that are like 1 over the system size. Those corrections vanish in the large system limits. We're looking at finite but large systems. And so we're looking at how that correction scales differently as we move toward the thermodynamic limit.
Yes, first here. So one suggestion, one question. So the suggestion is, since you have the experimental setup, so can you show us the data? The second one is, so what is the minimum size of your
reservoir or your bath to actually have this thermalization process with this non-communicating properties, charges?
I tend to think of a system as able to exhibit quantum many-body thermalization, some key signatures of it, if it's at least, so if we're talking about qubits in particular, if it's at least 8 sites long. 8 sites is about the minimum size at which we tend to see level statistics, such as energy level statistics characteristic of chaotic systems, level repulsion, GUE or GOE level statistics. So I would start at 8 sites, and the experiment went up to, I think, 21 sites. What was the first thing you asked?
So what experiment did you have? Was your collaborator?
Yes, I have a seminar about the experiment, and that has the data. I don't have it in the colloquium because it was more of an overview of the whole field, but I'd be happy to send you the paper.
I just have a clarification question. So you said that the corrections go as n. Shouldn't they also depend on like the environment size and the system? I mean, if you have a finite chain, shouldn't that only depend on, or it should depend on like the system that you choose and also the environment for the entire finite chain?
So the corrections go like. Whenever the global system size and
Square root.
the reason we can see the reason, for instance, by considering how. Okay, so we're comparing the thermal expectation value to the time averaged expectation value. So suppose we look at the thermal expectation value. This is the trace of our favorite operator with the thermal states of the whole system. That's how it's defined. So we want to calculate this integral. And so this trace, it's a sum over, say, the energy levels. That turns into an integral, which has a density of states. And that density of states depends on the size of the entire system. So this trace is an integral that is kind of over all of the states of the entire global system. And that's what ends up controlling the scale.
The system and the environment both?
Yeah, the system and environment composite.
So the n correspond to the entire chain?
Yes.
I see. Okay, thank you.
So for the interest of time, we have a last question here.
And the last question will be the worst question. One concrete example, at least at the one loop level or even on the lattice and non-abelian theories, where the charges are local, is asymptotic. When we have a run, the beta function goes negative on you, or the theory becomes more free at higher energies, so to speak. So is there any, obviously, since you work with Mark Srednicki and he knows this stuff very well, any commentary about that, about sort of like the sort of, running of coupling constants due to non-abelian charges, and the example here with thermalization?
I'd love to be able to make a connection from this thermodynamics to that high energy physics. So far, we've basically just identified this as an opportunity and not gotten into it. But I think we really need to.
Okay, on this note, let's thank our speaker again. And if there are still questions, please comment, approach Nicole directly here. Thank you.